Hello everyone, my name is Matour from Queensland University of Technology. My research topic is natural ventilation of double skin facade, evaluation of wind-induced airflow in tall buildings. Double skin facade system is a well-known building envelope, which has been designed originally for cold and moderate climate. But recently, we have seen several buildings with double skin facade in cooling dominant climate or warm climate. The reason is that this system can provide the opportunity to install external shading device, which is very useful to reduce direct solar radiation. But double skin facade with external shading device can actually increase the cavity overheating risk as a result of solar radiation absorption by slat blinds in between two skins. We know that the total heat gain of the building will be reduced by cavity overheating, can reduce the efficiency of the system as well. For adoption of double skin facade for warm climates, we can keep a shading device in between two skins, and on the other hand, work on cavity overheating risk reduction by increasing airflow rate in the cavity. We can look at DSF airflow path and DSF geometry to solve this problem. Comparing the conventional type of double skin facade and proposed double skin facade for warm climate, we can see that in conventional double skin facade, ventilation is as a result of buoyancy-driven airflow. But we need a stronger force for cavity ventilation, which could be provided by wind-driven airflow. These two configurations with lateral opening and lateral and front opening can increase airflow rate and wind-driven airflow into the building cavity. In this research, we are going to compare these two configurations' performance regarding ventilation in the cavity. For this purpose, we use CFD simulation in ANSYS Fluent. We conducted this simulation on a small scale tall building and validated the result against wind tunnel data. Simulation variable was a DSF configuration, wind velocity in 3 building levels, and wind direction as 0, 30, 60, and 90 degrees. These are the contours of the velocity that shows the airflow around and in the cavity of the building, and how the airflow entered the cavity and will be distributed. But for ventilation performance assessment, we use 3 criteria: wind ratio or normal velocity in the cavity, air distribution in the cavity as uniformity, and volumetric airflow rate of the openings. This figure shows the comparison between M0 with just lateral opening and M1 with lateral and front opening. This is the result of total airflow rate into the cavity. As you can see, the airflow pattern in a DSF with a lateral opening is highly sensitive to the wind direction, so it can change from 30 degrees to 60 degrees very sharply. Creating a front opening can be a potential strategy to encourage airflow into the cavity for a wider range of wind directions. This graph shows the performance of front opening in terms of airflow rate into the cavity in just this configuration. As we can see, the front opening at 60 degrees is not as effective as 0 and 30 degrees, and almost all the induced fresh air is provided by the lateral opening. When the wind direction is at 90, the front opening works as an outlet instead of an inlet. So in this direction of the wind, front opening cannot be efficient, cannot be effective for improving the ventilation in the cavity. This graph shows the wind ratio and air distribution in the cavity. As you can see, in M130 and M190, despite the volume airflow rate increase through the openings, the airflow cannot be distributed evenly across the cavity. So there is still a risk of cavity overheating in one part of the cavity, and it's not ventilated efficiently. Regarding this issue, for the future work, we are going to evaluate the effect of front openings arrangements and cavity size for proposing the optimum configuration capable of efficient ventilation in wider range of the wind directions. Thank you for your attention.